Okay, so this is an additional video for chapter 14. I'm going to focus on um, rice tables specifically in this video. There's two slides I have to start out with that are not rice tables, but the rest of it is rice tables, and kind of doing some things I would have done in class to give you a feel for how to go about solving these rice tables, which is really important. The first thing I want to talk to you about is just the equilibrium constant and getting comfortable with how we're deriving it. When we say it's the equilibrium constant here would be the concentration of C over the concentration of A squared over the concentration of B. These brackets mean molar concentrations. Now you can write equilibrium constants in terms of pressures or whatever, but a true equilibrium constant, I can't go into this in this class because it's beyond you. You might cover this in PChem, but is derived from activities. What you have to realize is that all of these are fractional, if you will. What I mean by that is even if we say it's 2 molar, which is not fractional, it's a whole number, 2 molar concentration, that is 2 moles in a liter of solution. And you can convert that volume of water, the amount of solvent that's in that liter of solution, to moles. And this will be a mole fraction, if you will. So it's not 2 moles, it's 2 moles in a certain molar volume of water. So you have to think about these as all being fractions. It's no different if it's pressures. If this is 2 atmospheres, this is 1 atmosphere, and this is 1 atmosphere, this effectively is a partial pressure. It's 2 atmospheres over a total of 4 atmospheres for all 3 gases if these were gases. So what I need you to realize is that these are fractional. If you treat them like that, then this kind of makes sense in how the equilibrium comes about being, squared. And just like we said before with rate laws, these are like rolling dice. Let's say B is a 6. So the possibility of rolling 6 is 1 over 6. And let's say A is a possibility of rolling a 1. Okay? Well, a possibility of rolling a 1 is 1 over 6 also. But now we have to roll with 2 dice, 2 ones, right? So it's 1 over 6 times 1 over 6 times 1 over 6. So effectively it is B times the concentration of A squared. If this had been a 3 here, it would be 1/6 to the third. So you can do this because this is not a changing rate. This is at equilibrium. So the rates are equal. The forward and reverse rates are equal. Concentrations are no longer changing. So unlike writing a rate law, which has to be determined experimentally or written from elementary steps, once you understand the mechanism, an equilibrium constant can be written from a balanced stoichiometric equation because we've reached a point at which the forward and reverse rates are equal and that the concentrations are no longer changing. You cannot do that with a rate law because the rate is changing and the concentrations are changing. So I just want you to realize that this is, really just kind of looking at statistics and why this writing an equilibrium constant works this way. The other slide I wanted to talk about before we go into rice tables is Le Chatelier's principle. And I think the idea we've talked about already, if you add some product, then it shifts back and gives you more reactant. I think that's easy enough to grasp. I wanted to deal with gases and dealing with volumes and pressures. So, if we say volume is doubled, okay, that's the same thing as saying I've halved the pressure, right? So if the pressure decreases, we can make this very simply. You can look at this as if you want to calculate Q and to see what happens. So the system's at equilibrium, okay? Then I'm going to double the volume. Let's just say for the sake of simplicity, to make it easier for us to do, is that the pressure of this at equilibrium is 2 atmospheres and at this is 1 atmosphere. Now, I just made them the same as the stoichiometric coefficients for convenience and easy thinking. But obviously, it doesn't have to be that. Equilibrium constant could be anything. All I know could be 10 to the minus 2. I don't know. So, at equilibrium then, if you will, the equilibrium constant then will be 2 squared over 1, which is equal to 4. Now what I'm going to do, I'm going to half the pressure. Okay? If I half the pressure by doubling the volume, I now have I now have 1 squared over 0.5. This gives me a value of 2, which is now my Q. You can see that Q is now less than K, and therefore, to respond, it's going to want to produce more product. So that's one way of looking at it. Now, it's easier to think about it the conceptual way, saying, hey, I've doubled the volume, which is going to reduce the concentration. Therefore, the system is going to want to increase the concentration, and does that by moving in this direction because it produces more particles for the same given volume, right? So it produces more particles in this direction. That will counteract that decrease in concentration. And you can use the same reasoning here. We're going the opposite direction. We're increasing the pressure by having the volume, so the concentration is increased. We're going to want to move in this direction to decrease the concentration. You can also calculate Q there to convince yourself of what's happening. That's why if there are 2's here and here, or 1 if you will, because that would reduce to 1's and 1's, nothing happens if I change the pressure or the volume, because neither side favors a higher or lower concentration. So it only works if those stoichiometries are not the same. So I wanted to emphasize that because it maybe didn't come across so clear. So now what I'm going to spend some time is talking about Rice tables. And these were examples straight from your slides and from your videos in some case. So this is a reaction of H2I2 going to 2HI, and you're giving these initial concentrations. You want to determine, in this case, the equilibrium constant. In many of these examples, you're going to be given the equilibrium constant. You're going to be asked what's the equilibrium concentration of these species. But this one we want to determine Kc, but I just wanted to show you the table so you know how to structure these tables. Because the question I get in class sometimes is, well, why is this one 2x and why are these negative and this one plus? Well, what we're going to do is we're going to look at the initial concentration. We're starting with this and this and this. So if the reaction starts with all reactants and no products, we have no choice. We have to move in the direction of forming products, which means this has to be plus and these have to be negative. Okay? If we had started with all product, then this would have to be negative and these would have to be positive. But we're starting with all reactant. Now, since we're starting with reactant, the reactants have to disappear. So this is a negative here, and this is a negative here. And this must be a plus because that's going to increase. And to get this line down here, this is your rice. Remember, it's reactant, initial, change, and equilibrium. That's what the rice stands for. Your reaction is here, up top. Here's my initial, change, and equilibrium. To get this, you just add these two columns together. So you get 0.01 minus x, 0.008 minus x, and 2x. That's how you get your equilibrium concentrations. Now, in this particular example, we're starting with all product. Once again, there's a 2 there. This now has to be minus 2x. And then we get this. These have to be plus x. And then you can go in and plug in, and you can solve. And I went through the solving of this is in the slides. I want to really teach you how to set up Rice tables. Okay, so I want to share something with you in case you come across this. Let's say, as a separate example now, we start with some of this and some of product. How do you know which direction it's going in? How do you know whether you're going to have negatives or positives in your change column? Well, what you need to do is calculate Q. And you can calculate Q because you've got all the concentrations and then compare it to K. And once you calculate Q, just remember to square this one. It's going to be 0.05 squared over 0.1 times 0.1. Once you calculate Q, if Q is less than K, then you're going to form product. And that means these would have to be negative and this would have to be positive. If Q is greater than K, then you're going to have to form reactants, and then effectively this would be negative and these would be positive if Q is greater than K. That's going to be key. But once you get your expression like this down here, you can go ahead and solve this. And that's what was done here. Now, just to explain this in case some of you are confused, we have a plus or minus roots here, so we have to solve this both ways. So if you look at the plus root, I'm going to do the plus one first. Let me erase that so I can emphasize that. I'm going to do the plus root first, just the plus root. So I now have this plus a negative 2x, right? Because it's the plus root. To bring over a negative 2x, I have to add it. That's how I'm getting this here. And then, of course, this is in the plus root. This is going to be over there, so that stays there, and that's how you get that root. And then you can solve that for x. For the negative root 1, this here, this becomes plus 2x, and when you bring it over here, you subtract it, so you get this. And then, of course, since it's negative, this is going to be negative, and that's how you're getting that, and you solve it. Ultimately, we said I don't know if I said it in the video, but it's in the slides, that you get rid of any negative root because x cannot be negative. It makes absolutely no sense. Now, if you have two positive roots, typically what will happen is that one of them, when plugged in here, there's a different color here because when plugged in here, will wind up giving you a negative number down here somewhere. It won't make sense. Let's say that x turned out to be 0.2 on one of my roots. Well, that's nonsense because 0.1 minus 0.2 is going to give me a negative number. So if x equals 0.2, that can't possibly work because this will wind up being negative, and so will this. And this. So in some cases, you'll get two positive numbers, but only one of them work. And say the other value of x was 0.002, well, that can work because that'll still give me all positive numbers down here, which is what I need for equilibrium concentrations. Okay, so here's another one, solving Rice tables. And this, I wanted to just show you the quadratic. In this case, we've got a situation once we plug it in and we solve everything. We get this, and then, of course, we're going to have x squared over 0.1 minus x. We rearrange that, we wind up with this quadratic equation. You got to put it equal to 0 to get your quadratic. This is reviewed in your appendix if you need help with the quadratic equation, but also you can just Google that. You're going to have tons of sites on quadratic equations. So how do you solve that? Well, and I've color-coded this. So I've said that a is the coefficient for the x squared term, b is the coefficient for the x term, and c is the non-x term coefficient. In this case, c is going to be negative because the form of the equation is plus c, so that means c has to be negative. And you're basically going to solve this two ways. And when you do that, you'll get two different numbers. And once again, ignore the negative root. There it is there. That's what I was looking for. Ignore the negative root. We can't have a negative root. Can't have a negative concentration. Then you get your concentrations, and we check our work by making sure our Kc is equal to 2.5, which is what was given to us up here. Okay? So that just takes practice solving the quadratic. And, if you get a quadratic on the exam, there'll be one of them. That's it, because they take some time to solve. Now, I want to show you a shortcut. In some cases, we get reactions, and here we are with initial concentration. So if we were to do this table, we would have, plus 2x, minus x, and minus x. So you get 0.79 minus x, 0.21 minus x, and 2x we get for our table, right? And once we don't need this 4 here. I did make this change. For some reason, it's not showing up. But anyway, once we get our expression here, solving the quadratic equation. I'm not going to show you the solving of that. You can solve it on your own. Solving the quadratic equation. Don't forget, though, this is going to be 2x squared, so 2x squared, so you get 4x squared. Once you put it in account for that 2, you need to include that there. And this 2, these are separate 2's. That's what I want to make clear. Just because you have a 2 here doesn't mean you stop squaring it for this. Okay, you still got to put it into the equilibrium expression. It means the 2x goes in here. And when you solve the quadratic, you get this. Okay, now I want to show you a shortcut. Ultimately, this is the equation we came to right here. There's a rule of thumb that says if your initial concentration is greater than 500 times the Ka, you can make this assumption, and that is that these x values are going to be small enough. What that is if your initial concentration is much greater than the Ka, 500 times the Ka, that means x is going to be small. So what we're going to do is basically say that this is small enough that these concentrations are just going to be what they are initially. Okay? So you just look at your Ka, whatever it is, it's 1 times 10 to the minus 5, multiply it by 500, and 0.21 is still greater than that. I used the lesser of the 2 here. So that, 500 times that, this is at 10 to the minus 5, so you can actually see this. You don't have to do the math. That simplifies the math tremendously. When you get rid of those negative x, you don't need to use the quadratic anymore, and you can simply solve this now very simply and look at what you get. And compare that to the original answer solved by the quadratic. To two significant figures, they're exactly the same. 6.4 times 10 to the minus 4. And I would argue that in many cases, this is okay. 100 times the Ka. If I'm doing a multiple choice exam, I'm going to do this. And that assumption will hold. That only gives you about a 5% error. And most of the time, with multiple choice, questions are going to be very different. If you're doing a quick estimate, you just want to know quickly, hey, what the equilibrium concentration is. Just do a quick little estimate, 100 times the Ka, you can make this assumption. So I'm going to tell you that, hey, even 100 times the Ka, now that might not work for smart work if they've got a question in there and they expect you to use the quadratic. So just be aware of that. But I want to give you that rule of thumb that if you've got a quick calculation you want to do, if you're taking an exam and you want a quick route to an answer, that's a good approach. And the last slide for this additional video here is just this famous important equation. I just want you to think about this a little bit. Let's imagine we have a really exothermic reaction with a negative delta G naught. That looks like this, right? Remember what delta G naught is. Delta G naught is really this and this, right? That's all it is. Hey, if you start with all reactants, yeah, you're going to move towards products if you start with 1 mole of each, okay? Now, if you start changing those concentrations, have very little of one of them, that can mess with whether or not you'll reach equilibrium or not. You might have a limiting species. But if you're just dealing with basic concentrations and you've got enough of each of those, delta G naught will tell you, hey, yeah, you're going to form product. But delta G tells you whether you're spontaneous at any point along that way. So remember, now look at this equation. It's the sum of these two, and this is Q here. So let's say we're way up here in our reaction, okay? Now, we know that delta G naught is negative. We know in this case we're going to have mostly reactants for Q, which means this number is going to be less than 1, much less than 1. It's going to be fractional. And when you take the natural log of something like 0.01, you get a negative number, which makes this even more negative. You see? So as this moves along here, Q gets less and less negative. Eventually, it'll become positive. And eventually, if you're over here, you could very well get a positive delta G, right? You've reached a point at which this is where it's 0. Anything over here is positive on this side, which means it's telling you that you're past equilibrium when you look at it from a reactant to product standpoint, and you'll be moving in this direction to get to equilibrium. That's what the point is, that value of Q will be greater than the value of delta G naught. And the Q will be positive at that point, making your delta G positive. So that's important to realize that delta G is at all these points along this line. So it tells you spontaneity at any instant, under any situation. What are the concentrations? What are the temperatures? Right? Because you got a temperature. Delta G naught is simply for 1 molar concentrations at 25 degrees C. So that's really critical that you understand this equation conceptually. With that, that's the end of this additional video.